Uh, Hello, good afternoon to all. Good afternoon. So, today we have third lecture, and today we'll talk about the PNR data analysis part, and then application of the polarized neutron reflectivity. So, so yesterday I just touched upon these three things, which is called a bit practical issue in reflectometry. And I told you, since we have this reflectivity falls as 1 by Curie square 4, so we can measure up to a particular Q value only, this reflectivity pattern, because then signal to noise ratio becomes 1, and then we cannot trace out the signal from the background. Okay, and this Q maximum which we can achieve in our reflectometry will decide our minimum thickness of the single layer, and that relation is there, d equal to 2 pi by q. That is real space to reciprocal space relation. Okay, and another thing I said, the geometrical effect, or we also say footprint effect, where at low angle of incidence, when your beam size is greater than your sample size, then whole beam doesn't fall or make that by sine theta and multiply to the make it reflectivity pattern. Okay, and another thing which is very important is called instrument resolution, and instrument resolution is defined as this delta q by q whole square equal to delta lambda by lambda square and delta theta by theta square. As I said, the source for this wavelength spread in case of reactor source or monochromatic beam comes from the monochromator, because if our monochromator is not perfect, then we'll have this delta lambda. And for different monochromator like graphite, it is about delta lambda by lambda is 1%, and we are using silicon monochromator over here. We have very less because we don't have that much. We have a little bit perfect single crystal in case of our case silicon. Okay, and then delta theta by theta is called angular resolutions, and it comes from the as written over here, delta theta is slit width. The collimator we use, the collimation, as I said, we have a neutron absorbing material, and we make a this is a major contribution in case of reflectometry. Okay, so and here in this figure I have shown a reflectivity pattern plotted as for different resolutions, delta q by q value, and you can see for 0.02, which is very good resolution. We have nice oscillations, but this oscillations get smeared out when we increase this value, or when we make our instrument resolution poor. And as I said, the maximum thickness, again I'm saying this is single layer thickness, not the multi-layer thickness. Okay, single layer thickness on a substrate, and that is the maximum thickness we can study from this instrument or in any instrument, depends on the resolution of the instrument. Again, 2 pi by delta q. Okay, so this two things is very important. Example, yeah. glass substrate, then nickel. We have glass substrate. So this is a multi-layer sample, and we do polarized neutron reflect. We do here. I will just consider with this analysis. I will just say unpolarized, but we can do polarized also. So for unpolarized neutron, we have just one reflectivity. Okay. And what I was saying, the geometrical effect comes to play in this region. So when you measure reflectivity pattern, your patterns looks like this. It is almost one. This is called geometrical effect because neutron falling on the sample is less than the incident. Sample is multi-layer. Now you see you have these kg oscillation, like you count them. So if your multi-layer is good contrast one, then you will have all this kg oscillation, and you can count them. This is 1, 2, 3, 4, 5, 6, 7, 8. So yesterday I told you n minus 2. So n is number of bilayers. So we have 8 here. So we'll have 10 bilayers. So, and from this, what is the Q range for this? If you see the Bragg-Peak Q range, you will come to know what is the bilayer thickness. So if you do 2 pi by this 2 pi will give you the bilayer thickness, and what is the delta Q between two kg oscillation will give you the total thickness. So without analyzing the neutron data, if you have a perfect, so it is bilayer, both of them, it will be the combined effect of them. Okay, but other things like what is the peak, total thickness is the total thickness between these the delta Q between two kg oscillation will get, and this kind of information you can. But what is the layer thickness of individual nickel titanium? What is the density of individual nickel? What is the interface roughness? These things you will get when you will do the data analysis. And any scattering techniques where we measure intensity, actually we lost the information of measurements. So we have just reflectivity, and that even up to a definite Q range. We don't have whole Q range. And you know the relationship between real space to Fourier space. When we want to get the real space information from Fourier transform, then we need minus infinity to plus infinity. Now, I mean, because that integration is minus infinity plus infinity means we need whole data range, but we don't have ideally. In experiment, we have a limited data. Same for this reflectivity also, like any scattering technique. So what we do, we uh, we don't have phase information, we don't have amplitude, we have just intensity. So what we do, we model the data. So model the data means what we know how we have grown our multi-layers. We know we have grown 10 bilayers. We our thickness is like, we give the guess value. So initially, what we will do in the modeling of data, what we do, we make an input file, like from our on which reflectivity pattern depends. Uh, okay, so what are those parameters? Yes, density of each layer, thickness of each layer, or interface roughness of each layer. These are the three parameters which we can get from unpolarized reflectivity as well as X-ray reflectivity. And if you have a magnetic sample and you have polarized neutron reflectivity data, then you have the additional parameter which is called magnetic. So you make for each layer these information available, make an input file. Then what we do, we generate a theoretical reflectivity pattern from these input files. Okay, and because I said any instrument has a resolution. So whatever data we are getting, it is convoluted with the instrument resolutions. So for comparing the data, theoretically generated data with experimental data is not possible just by comparing that way. I mean, if you calculate reflectivity and you have experiment, you just can't compare both of them. You have to either deconvolute your experimental data or convolute your theoretical data with the same resolution parameter, and then you can compare the both of the data, both of the plot, and that comparison is required for model fitting. Okay, and one of the method for convolution is given here. So suppose you have theoretically you have generated reflectivity at particular, convolute that reflectivity pattern, convolute that within this minus infinity plus infinity is minus delta q plus delta q. That is the instrument resolutions. Okay, so it should not be minus infinity plus data point if you generate plus delta theoretically. Then for each q value you have to convolute with the instrument resolution, then you can compare that convoluted reflectivity pattern with the x-ray minimum. uh, we can say we have these are the our results, and as this is any model fitting won't solve, it will give you one solution. Okay, so that way, and from other technique you can say, I mean, because you have grown these films, so you will say okay, if it is what to do to generate theoretical reflectivity data, then convolute with experimental resolution. Then you have experimental data at each q, theoretical reflectivity with convolution at each q, and then you calculate this chi-square, which is defined over here, which is nothing but the difference between experimental and reflectivity, and then what is the error on experimental data point. Okay, and you minimize this. What does it mean? You are making this difference that you do iteration, like you change this parameter and achieve the minimum difference between the experimental and theoretical reflectivity pattern. And this is we do for any uh, suppose chi-square. I have just your chi and you have one parameter, suppose thickness, and the chi-square and thickness, these parameters vary like this. Okay, so what we do for chi-square minimizations, there are so many methods. One is called gradient method, where you take delta chi-square by with respect to some function and you follow the negative value of that. I mean, you are negative gradient you are following. Means what you doing, if you have a guess value over here for that parameter and you calculate chi-square comes like this, then you take gradient of this and then you follow this path. Okay, and you will achieve some minimum chi-square. But when you do, there are other method also. So like gradient method, one thing I have written over here. So what happens if you have this kind of functions, chi-square function with a parameter, then it depends highly on what guess value, what the initial value you take. Because if you take initial value over this region, then you will be following during your iteration, you will be following this path for chi-square. So these local minima, sometimes it is very difficult to avoid these local minima. You may not reach that particular global minima, which is the best parameter you want to achieve. So there are other methods to do this. One of them is to do this chi-square. I have used for doing this analysis at reflectivity data at BRC. And what it does is, instead of taking one guess value, like as this name suggests, we have a population of the initial gas value. Like here I have shown 5 number. So initially we the number, and then it there are other steps like the genetic algorithm. It has a called crossover, mutations, all those things involved in this, and it it converts these parameters from all the uh, population of set of parameters. So there is high probability, if you do this, there is a high probability that you will reach the global minima in this case if you take this genetic algorithm. Okay, and this is one of the best technique, one of the robust technique where you can achieve, where you can reach to the global minima, and then you will get the parameter value that is the best suited for your curve. And there are so program may require scattering line density like input. Some may require scattering line density in angstrom -2 unit. Some may need in Fermi. So that may be the variant, but basic parameter are same. So one of is the GenX, which also use this genetic algorithm program to minimize your chi-square minimizations for reflectivity data. Okay, and I have written this PNRF, and if somebody want, they can write to me. Though this is not user friendly, but it is very easy to run and do the so so what basically what we do, uh, like we had this data over here. Suppose we take this data, as I said, nickel titanium, and we want to fit this data. This is make input data files. So my programs take this type of input data files. So as I said, we have 10 bilayers. So total number of layer is 10 into 2 because this is nickel titanium. So 20 nickel titanium layer, and then one air layer and another substrate. So total is 22 number of layers. So the like I want for unpolarized, I'll give 1. There is no spin for unpolarized, I have given 0. Then there is wavelength in angstrom for neutron, this 2.9 angstrom, and this is because I don't because I didn't get that, but my program itself get the scattering line density. How what are the parameter thickness we are giving? Suppose gas value we give nickel for 50 angstrom, titanium 50 angstrom. Okay, first this is substrate over here bottom. We have a glass substrate, so density of glass in the second column. This is in kg per meter cube. Then we have to give. Sorry, this is not Avogadro number. This is atomic number. Okay, this is atomic number over here. This is atomic number for glass SiO2. Okay, this is B coherent. This is absorption part of value, and this is magnetic moment. Since we are doing unpolarized, so you can see 0.00, and then this is roughness in angstrom. Okay, so from these two, density and Avogadro number and B coherent and B observation, these 4 columns, you can, I mean, in different program, different inputs are required, and these 4 columns give you the scattering line density. So instead, for maybe for some program, you have to calculate the scattering line density and give only one parameter. But since my program generates scattering line density in the within the program, so I give this kind of input. So basically, this is nothing but for each layer, what we are giving these parameters: thickness, density, and be coherent, because this is scattering line density and roughness. And like this is thickness 50 angstrom. Again, for titanium, we are giving this one. Okay. And since this is multi-layer, this is a repetition. So we have repeated for all these things. So this, if we take this gas value and generate the reflectivity pattern and compare with our experimental data, how the pattern will look like. Okay. So it is here. So if you say we have 50 angstrom, nickel 50 angstrom, density profile over here. This is for nickel, titanium, it is negative. Okay, and this is 10 by 11. This is surface interface, and then this is depth. So this is glass substrate. And you can see the reflectivity pattern. And here we didn't consider also. You see nice, very big oscillation. We didn't consider the instrument resolution also. So we have just taken theoretical reflectivity pattern to compare these two. So this is too much off. Okay, our guess value. But we have a multi-layer, so we can improve on that. So what we will do, during iteration, we will change this parameter, thickness, roughness, scattering line density, as well as we have given proper resolution for instrument resolutions, which will convolute and then compare. Now see, suppose we gave that run and we got this input file. So initially we have given 50 angstrom, 50 angstrom. Now during the iteration, we have got 56 angstrom for nickel and 36 8.8, and this is 4.5. And you see roughness becomes 8 angstrom for titanium, and for nickel it is 9.6 angstrom. So this is pattern will look like when these parameter has been changed during the iteration. So you can see here, this is during in between the iterations, when it is almost giving the these kg oscillation are matching. Only the intensity parts is not matching at higher Q. It says that the roughness is not properly adjusted. Otherwise, thickness, because the peak position is coming same, these kg oscillation are matching. So peak, so it says thickness is all right. Okay, but only maybe we have to play with the roughness parameter. It has to come down, this theoretically generated reflectivity, and this is the output scattering line density. So nickel, titanium, you can see roughness has increased, and we have given proper instrument resolution. So this look nice. So now again, if we vary now roughness and keep those parameter constant, like thickness 36 angstrom, 56 angstrom, density also same, only just vary roughness, the best fit we will get is the higher roughness. For iron is 23 angstrom, and for nickel it is 23 angstrom, and titanium is 13 angstrom. And this gives you the best fit, and you can see nicely matching over here. And this is our final out. So this parameter is our result, because this is giving the best. This is giving the minimum difference between experimental and theoretical, and this is giving best fit. We say this is best fit. Okay, and so this way we do the data analysis. So what we did initially, we took some this was our scattering line density over here, this black one. Our corresponding reflectivity was like this, and we didn't take the resolution factor also into account. But in the second case, we took the resolution factor account, and we vary the thickness. Now you see thickness has come down. So 50-50, it becomes 56-36, and then final. This is the final scattering line density for nickel, titanium, multi-layer, and this is the fit. So these are the steps, how we do the analysis, and then we report. This is our final result, because this is giving the best fit for this data. Okay. So this is the typically we do the analysis of the neutron reflectivity data. So if we have this polarized neutron, then we will have two reflectivity pattern, one spin up, another spin down. And then we will, in the input file, we have to give the, for nickel it is the magnetic, then we have to give the magnetic moment of nickel here, and also vary this one during iteration, and then try to fit both of them simultaneously. We cannot fit like spin up with some other moment and spin down with some other moment, because nickel moment, single moment for a layer, is responsible for both R plus and R minus intensity. So we don't have to give the two different magnetic moment for R plus and R minus. Okay. So this is the kind of analysis. Okay. So let us see now application of neutron reflectivity. So neutron reflectivity has application both the field, like biological or soft matter, as well as the magnetic, hardcore magnetism, interface magnetism. because in biological sample, and when we do biological sample, mostly we are doing unpolarized neutron. Okay, and biological sample, when we say we sometimes we come across the, like, we have a solid film, solid substrate, and then a liquid film, and that kind of sample we cannot put vertically. So we should design an instrument which can uh, do neutron reflectivity in a horizontal sample. Okay, so it is shown over here, you can see. So our sample should be horizontal, because that liquid, because biological sample mostly contain the liquid and other thing also, so that we cannot put vertically. Okay, so we have to, there are especially designed instrument for biological sample. If we are doing reflectivity from biological samples, that is called horizontal sample based reflectivity. And in any facility abroad, if you see, there are both kind of reflectometer are there, for biological sample, for magnetic sample. Okay, depending on the design. And why this is neutron reflective? It is elements like carbon, hydrogen, nitrogen, oxygen, and all the biological samples contains these elements. Okay, and so the kind of studies already has been done by people is kinetics, like protein unfolding, so polymer structure, how this unfolding happening, how this depth dependent, is there any layer structure, so what is happening when the protein fold or unfold, what happens. So this kind of information one can get from reflective. Okay, electrochemistry, like you are doing electrodepositions. Okay, and then how this nucleation is happening during the electrodepositions, how their roughness is influencing when you get change. Study also people do with neutron reflectivity in biological sample. Surfactants, okay, like liquid-liquid interfaces, like self-assembly, like one of the film I have shown here. This may be the lipid bilayer over here. Making a bilayer here, this is a monolayer here. Why only one monolayer? Why this kind of structure? Can this is come as hydrophobic and hydrophilic? Okay, so because this kind of structure happening. So if you want to know the structure of depth dependent structure of this biological sample, you have to do reflective. And because X-ray won't give you contrast for this carbon, nitrogen, hydrogen. And if you do neutron reflectivity, you will specifically see what is this layer. I mean, whether this is carbon, hydrogen, nitrogen, what is lying in this region, what is lying in this region. All these things you can distinguish from neutron reflectivity. Okay, so it is very important to do biological sample with neutron reflective. Okay, and for hardcore magnetism, we need a polarized neutron, and there are so many things we can do using polar. This is the, I would say, for depth profiling, it is the, because it can give the buried information interface. Nowadays people are saying interface magnetization changing, like you say, you have two antiferromagnet, you make a heterostructure of two antiferromagnet oxides, and at the interface you get the ferromagnet. That you can, that location of that ferromagnetic layer at the interface, you cannot get from any other technique. You have to do polarized, because other technique, like you do, like this macromagnetic technique, the BSM squid, they will say, okay, you have some ferromagnet, but where it is, then you have to do if you want to find that solution, where that ferromagnet is coming from, two anti-ferromagnetic, two ferromagnetic is coming, then you have to do like, and you know, in thin films and multi-layers, there are so many applied things where these phenomena like exchange coupling, when two ferromagnetic layer are coupled anti-ferromagnet, when you separate them by some oxide or some layer, this has a special application in memory. Okay, is there, you can also get from this PNR exchange bias, when there is a pinning of particular moment at the interface, the hysteresis loop shift in one of the magnetic direction, magnetic axis, field direction. That is the exchange bias. GMR material also you have both parallel and anti-parallel coupling between two ferromagnetic layers separated by non-magnetic layer. Okay. And this has a wide application in this memory devices applications. Okay. And then there is a proximity effects when you make a superconductor and ferromagnet, all the biology. So some of things we have listed here, like ferromagnetic films and magnetic coupling. These are the different things. In this case, we usually do the vertical sample, but there's no harm. We can use the horizontal geometry also. There's no problem doing this because this kind of application you do with both horizontal sample as well as the vertical sample geometry for neutron reflector. Okay, so you will find few of the instruments are horizontal sample design for polarized reflectivity also. Okay, so very sensitive for interface magnetization. You can get the information of 1 nanometer or less than sub nanometer depth or interface layer, which is nothing but two unit cell, two monolayer of that uh, element is so sensitive for that. Exchange bias, proximity effect, all those things, and very weak effect. Like you have very weak magnetization out of the interface, like 1 EMU per cc. The PNR is very sensitive to all these things, so we get the information on all this. Okay. So let us see now one of the example for biological sample. Okay. So this sample is they have made a lipid bilayer. They want to see the structure because this lipid bilayer is very close to the this membrane cells. Okay, and people want to study how it function, whether the structure of that bilayer or lipid bilayer or this membrane, how it affect, how it function, what will happen if we do something with that. So this kind of study. So one of the study which I have taken from the literature, because I don't do biological sample over here, I do magnetism. So I do polarized reflectivity. We have vertical sample polarized reflectometer at BRs. Okay. So one of the this example I have taken from this literature over here, where uh, where this sample, what they have done, they have silicon on silicon oxide is the substrate, silicon substrate, and then they have native grown silicon oxide on silicon substrate, and then they have grown lipid bilayer, one bilayer on. Okay, lipid bilayer, and then water is there, and then they took the neutron reflectivity, and neutron reflectivity is this blue things. Okay, but when they put a peptides, okay, on this sample, and then interaction happens with this membrane, and they got this reflectivity pattern, this red one. Now you can see from the, just look from the reflectivity, you have this additional feature is coming here, this oscillation, and also reflectivity is going down. So by looking itself, you will say at higher Q you have reflectivity is going down, means there is increase in interface roughness. Okay, and you can see the scattering density profile. So this is the surface, and this is substrate. So in first case, this was the water, and then there is a lipid bilayer, and there is a roughness showing at the interfaces, SiO2, and then silicon. Okay, but when you added little bit peptides on this, what you got? You have got this roughness as increases. Okay, at this interface, as well as this roughness has increased at this interface. Both the interface, the roughness has increased. And if you see, and then if you see what kind of structure they have set for this is like, so this is the bilayer. Okay, this is inner layer, outer layer, this is a lipid bilayer, this is silicon, this is silicon oxide over here. Okay, so different thickness, and this is scattering density showing that one. So this is lipid bilayer, and these are the interface. You have roughness over here, you have roughness over here, this is showing over here. Okay, this is the first case when you have just lipid bilayer. So when you put that peptides on this lipid bilayer, so that peptides interacts at the interfaces over here. See these things, and what happens, there may be little bit shrinkage in this layer thickness. it was around 33 angstrom, it becomes 29 angstrom. And there is an increase in roughness in this direction, because you can see they have shown very schematically how it is changing. Also, because of this peptides, there is an increase in interface roughness here also. So that reflects over here. The roughness increases means this becomes the density variation becomes at wider length scale. Okay. Also, in this region you have this one. So this kind of structure which influences property application of these things, and you will come to know what is the mechanism, working mechanism of these membranes and other things, which is directly correlated with the our cells and other things, can study by making this kind of artificial uh, uh, things where this lipid things closely match with the our uh, uh, biological cells. Okay, so this kind of study is I mean, being done and already done in biological sample. So there is, I mean, lot of things, as I said, has been done in biological sample using neutron reflective. Now, this was unpolarized reflective. So another question is, can we do anything using polarized reflectivity? Any biological things can we do? So here is the one example. So here, same bilayer things, this lipid bilayer, we have silicon, then we have grown a magnetic sample, permalayers. This is nickel iron. Okay, here this is magnetic, and then they have used gold, and then they have used this lipid bilayers, water lipid bilayers. Okay, now you have this magnetic, so you will have magnetic contrast. You will have spin up different scattering length density, spin down different scattering length. Here it is shown for this structure, it is shown the scattering length density for neutron. So you can see if you do polarized node reflectivity, then you will have silicon will have only this scattering length density, but for magnetic there are two scattering length density for spin one, spin down, and there will be the same scattering length density. But if you change this water with the D2O, then your scattering length density changes. So all these are called contrast variations. Sometimes you do this experiment with water, sometimes you do this experiment with D2O, depending where you will get maximum reflectivity out of your sample, and then you can say much more thing about your sample, about the layer structure of your sample. So yes, so answer is yes. Polarized neutron reflectivity will be very good, and it will give the additional contrast and give more I mean good resolution about your structure study, depth dependent structure. In fact, usually for biological sample. So now we'll take the polarized neutron reflectivity from magnetic films, and I will explain here two and three examples. First example, I will take iron germanium system. You know, iron is ferromagnetic germanium semiconductor, and it has a lot of application. Iron germanium. People were thinking for making a spintronic system like this, when you are controlling this spin dependent moment in this ferromagnetic semiconductor system. So, because just theoretically people say, okay, this will be a very good system, but when they studied it, they couldn't get the good result out of this. And what were the related issue for that? So, because they didn't consider there will be interface change, interface magnetization change to the interfaces during the growth. Okay? The another issue was there was formation of some magnetic dead layer. So what we say dead layer means no ferromagnetism at the interfaces. Okay. So sometimes we say depleted layer also, because what is happening? The ferromagnetism is getting lost at the interfaces. Okay. And there is a magnetic roughness also at the interfaces. These were the related issue, and we wanted to study this, and we had these kind of issue. So we thought, okay, let us do polarized reflectivity in combination with other technique and see whether we can see something. These we can get some solution about these phenomena, which is people just imagine that these are the factor which may be affecting the maybe possible application of this system. Okay. So we did X-ray and neutron reflectivity, combination of specular reflectivity and other techniques, and characterize this whole system. Okay, we use both bilayer and multilayer system, where we have grown silicon, iron germanium tri-layer on the silicon and multilayer on the silicon. And by sputting technique, we have used this, and other characterization technique for XRR, PNR, XRD is we have used. XRD just see to see the this crystalline structure. These results has been reported in this papers. So you see, let us take and now I just want to say reflectivity. You can also plot simple reflectivity like I said, reflected intensity divided by incident intensity is reflectivity. That comes 1 and then it falls 1 by Q. But sometimes to see the feature at higher Q, we plot this X-ray reflectivity into Q raised power 4. Q is here. So we multiply this Q raised power 4 just to give a weighing factor to see these kind of features here. So here also I have plotted same thing. X-ray reflectivity into Q raised power 4 in Y direction and Q in X direction. Okay, and you see we did X-ray reflectivity and we fitted this X-ray reflectivity. What information we got from this is this. This is depth profile, electron scattering intensity. We have this silicon over here. Then we have this buffer layer of germanium. Then we have an iron layer, and then we have top germanium. And what say this are the interfaces? We have this iron germanium interface, and this is germanium iron interface here. Okay, and this is nice. Uh, 3-layer structure is we have got from X-ray reflectivity. But when we did polarized neutron reflectivity, this red one is spin up reflectivity. This is spin down reflectivity. Again, I am plotting neutron reflectivity into Q raised power 4. Okay, and we fit this, and what we got, this is nuclear scattering density. As I said, we get two things: nuclear as well as the magnetic scattering density. So for nuclear scattering density, we got the same thing like we got from X-ray reflectivity, but you see the magnetic scattering density is quite different as compared to the nuclear interfaces. One of the interfaces very, lot of interdiffusion is happening at this interface as compared to this. So we get there is a asymmetric interdiffusion at the interfaces in this iron germanium bilayer. Okay, so from bilayer we found that the magnetizations at two interfaces are not behaving same. Okay, then we did same thing, neutron reflectivity from polarized, from the multi-layer sample, and this is unpolarized neutron reflectivity. You see nice Bragg peak over here, then K-zig oscillations, which are 8 number, and this is Bragg peak. This is unpolarized, so we have just spin up. We have unpolarized neutron, only one reflectivity pattern, and from this we get the scattering line density. This is nuclear scattering line density, and this is nice one. Iron has this one, and this is repeated. So this is we have silicon substrate, then germanium buffer layer, then iron germanium multi-layer, 10 bilayers. So nice structure. What we have drawn is shown here. We found from the neutron reflectivity. We did polarized neutron reflectivity. This red one is the spin up neutron reflectivity, and this blue is spin down reflectivity. And fitted is these cups. Black one is the fitted one. Okay, and then what we found that because iron is ferromagnetic, but we found ferromagnetism iron is not uniform throughout the layer. Here we are just showing one bilayer. There are 10 bilayers like this, but if you say one bilayer, we have iron in the middle region has magnetic moment of 1.3 mu b. At the interfaces, there is a reduction in the magnetic moment of iron. Okay, and germanium is 51 angstrom, which doesn't have any magnetic moment, zero magnetic. So what we found are two interfaces. We have different magnetic moment, which may be due to the asymmetric diffusion when we grow iron on germanium and germanium iron. Because one of the thing from XRD what we found is iron is crystalline and germanium is non-crystalline. So we found a detailed depth dependent magnetizations of this iron layer from this polarized reflectivity, which otherwise is not possible to find out. Okay, from other technique we can see. So another thing, another example is nickel titanium system, and you know this is a structural material. When you make the alloy of this nickel titanium system, it has a wide application. So what in this system, what we did, we know from X-ray reflectivity we get the electron scattering density, and from polarized neutron reflectivity we get the nuclear scattering density and magnetic scattering. And if we anneal this nickel titanium multilayer, there is possibility that at interfaces we get the alloy of nickel titanium. Sometimes this alloy makes amorphous compound, and we don't know from XRD whether what kind of crystalline phase it has, which phase of alloy has formed. So in that case, what we do, we have proposed this here. If we do X-ray as well as PNR, we can estimate exact composition of alloy, even the alloy is amorphous. How? Because we know from neutron reflectivity, nuclear scattering density. From X-ray, we know the electron scattering density. And if we have alloy has A, M, B, N, then this is nothing. This is from the experiment we can get. This is theoretically we say, suppose M time of element A or N time of element B for neutron. This is for X-ray, and we have two equations and two unknown, N and M. And from this, we get the Nm, and we will exactly know what is the composition of this N. And this exactly we have done for number of system. Here I'm just showing one of the system is the nickel titanium. Okay, and what is that? We have a multi-layer of nickel titanium grown on a glass substrate, and then we anneal it 300 degrees Celsius and 400 degrees Celsius and saw how this depth dependent structure and magnetization is changing on annealing. Okay, so this was the XRD data when there was S deposit nickel titanium multilayer. So we got nickel peak as well as titanium, both are crystalline. When we anneal this at 300 degrees Celsius, titanium peak has gone, so there is amorphization of titanium, but nickel film, this peak is also little bit shifted. Then we did this annealing is 400 degrees. Sorry, this should be 400 over here. Okay, it is not 300, and we got a nice peak around this. And this is not the nickel peak as well as not the titanium. This is some additional peak we have got. Then and this was not matching with any kind of alloy of nickel titanium, because there were overlap of too many alloys around this scattering angle. So we were not sure to which alloy it has formed. Then what we did accelerate. So what is happening? This is nickel titanium bilayer. When we anneal, we have alloy is forming at the interfaces. We did X-ray reflectivity. Again, nice bragg peaks are coming, and nice this bilayer repetition structure is there for S deposited. Then 300 degrees Celsius. So there is a modification in reflectivity data, and we found at the interfaces there is alloy formation happening. Okay, and then 400 degrees Celsius, then we have completely alloy forming at the interfaces. Okay, and then we did the polarized neutron reflectivity, and polarized neutron reflectivity you can see this is for as deposited R plus R minus, red one is R plus, blue one is R minus. Then at 300 degrees Celsius there is a suppress both the reflectivity pattern. The splitting means the difference between R plus and R minus intensity is reducing, and it goes off completely. Both R plus and R minus intensity at 400 degrees Celsius are same. And from this we got same nuclear scattering density like we did we obtained from X-ray. Similar nuclear scattering density we got, but what we got additional thing is magnetizers. So magnetic scattering density for SDP is nice. Nickel, it is a very nice one, and 0 for titanium. But when we anneal at 300 degrees, this nickel moment has gone down, and at 400 degrees Celsius there is almost no magnetization for this these films, okay, which are alloy. So what we found using, again as I said, both nuclear scattering line density and electron scattering density, we obtained this alloy phase is nickel 3 titanium. Okay, because we did same thing which I explained earlier, like this, like this. So from neutron we got this, from X-ray we got this, and M and N using these two equations, and we found this is the uh, phase alloy phase form on alloy, the nickel titanium. And also you can see from here what different time different crystalline structure, as well as this is correlation length. We did oppospecular reflectivity also. I am not shown here, but that is X-ray reflectivity, oppospecular. And from this we found how the annealing is changing this particular property of this sample. The next example is the oxide film. Okay, this is called magnite, LPCMO. LPCM, lanthanum, LaPrCaMnO3. Okay, and one of the composition of this LPCMO film, you know that the magnite film, this shows uh, first order phase transitions, and they show metal to insulator transitions. So if you do the resistance measurement on these samples as a function of temperature, at high temperature they are insulated, but when you decrease the temperature, then you get a transition over here, metal to insulator transition. During the cooling, it follows this one, this cycle, and then it becomes metallic in this region. Okay, when raise the temperature, then it follows this path, and then you have a hysteresis. Okay, and that shows the first order phase transitions, and this hysteresis things. So we have an insulating phase at high temperature, metal at low temperature, and in this region we have a phase coincidence. Okay, both metallic and insulating phase. And from the magnetization measurement, people have seen those metallic and insulating are nothing but the ferromagnetic and antiferromagnetic phase. Okay, and you can see the phase coexistence is also here at one particular temperature. We have taken this conducting AFM measurements from this. Okay, and you can say these blue one are the metallic. Okay, and this is insulating phase. So there is a phase coexistence happening when we cool down these systems. Okay, so what is the reason for these? So why we get this phase coexistence in this system? So there is a theory that there is a strain field. If you apply the strain, that strain field give rise you the this percolation growth of one particular phase when you decrease the temperature, and decreases the okay. So so there was the theory like this. So to find out how this strain changes our magnetization in this system, when we apply a strain, what happens to the magnetization of this film? Okay, because from this conductivity measurement we see it becomes metallic at low temperature, and there is a phase coefficient in this, and this metal is nothing but the ferromagnetic in the magnetizing study. Okay, so what we did in this particular system is we have taken this one sample of composition La27, Pr40, calcium 33, MnO3, and these are the thin films grown on the NGO substrate by pulse laser diffusions. I'm sure you, because if you are doing thin films, you may know the principle of the pulse laser diffusion. It is nothing but laser pulse are falling on the target, and then it remove that material and diffusion on your substrate. And in this case, this is the one of the technique where you get a very good stoichiometry. Well, I mean, during diffusions, the stoichiometry of your target materials remains same. So it is possible to grow such type of stoichiometric thin films by pulse laser diffusions. So we, as usual, we did we made the thin films. Then we did all type of characterizations like macroscopic magnetization by uh, speed magnetizations. We did resistivity measurements. Then we did TM, conducting AFM to see the electron phase. Okay, and in addition, what we did is depth-dependent techniques, one by X-ray reflectivity and polarized reflectivity. And in fact, this was the one of the experiment where we have simultaneously made. Oh, can you say how it has gone off? I guess I have done escape. Which one is that? It's gone off. Went off. It's good. Yeah. I'm sorry for this disturbance. So we did this transport strain and PNR measurements at the same time, and this is the experiment which is only doable with the PNR, because we have designed a mechanical zig and did polarized neutron reflectivity. And this mechanical zig, I mean, cannot be designed for VSM or scoop measurement. Okay, so that's what I was saying. With the different kind of sample environment is possible in neutron scattering time, which you can easily apply. Okay, so we made this mechanical zig over here. This is the small zig over here. This one. So this is called mechanical part, where we have put our thin films here. This is our thin film, and then we are putting is on top some stress, and we are bending our substrate. Okay, so we can bend this substrate, and this is on the our this cryostat cool head, and then we do we did polarized neutron reflective. Okay, and simultaneously we measure the transport measurement, resistance, as well as we change the temperature and magnetic field. Okay, so in principle, we can apply the compressive field when we put our substrate and then stress from the film side. Then we are we are compressing our film. Okay, by bending this thin films by adopting this configuration. And when we flip our sample on this mechanical zig, now film is down and substrate we are bending that way. Then we are applying a tensile strain, and using this we can really get the what how much strain we have applied on this. Because if you see here, this is the laser beam reflected from the film when there is no bending. But when we bended the reflect this sample and then reflected the laser beam from the sample, you can see there is a spread in this beam. So from these things, it's on here. From these things, we can get the radius of curvature and the kind of strain we have applied on the thin. Okay. So, and then what our transport measurements is. So we did this R versus T measurements. This is a typical metal to insulator transition in the system. But when we applied a compressive strain, then this shifts to higher temperature. And when we apply it uh, tensile strain, that shift to the lower temperature. So it says that on applying the compressive strain, your metallic phase go to the higher temperature. So we have chosen three temperature on these three cups. Okay, during the cooling as well as during the warming, and then we did polarized reflectivity for three cases: for when sample was not bent, when sample was bent with tensile strain, when sample was bent on compressive strain, and at a particular temperature of 78 K and 89 K while warming the film. And you You see, this is polarized neutron reflectivity while warming the sample for three cases. This middle one is when there was no strain. Bottom one was when there is a compressive strain, and top one is when there is a tensile strain. And you can see there is a the difference between these spin up and spin down reflectivity is changing. Maximum difference is there when there is a compressive strain. It decreases when there is no strain, then it further decreases when we apply a tensile strain. And what information we have got from this reflectivity pattern is, so this was the magnetization depth profile of our film. This is the LP CMO film. At the interfaces, we got lower magnetization. This is the middle of the film. This is the substrate side. Okay, so this is when there is no strain. Then this is when there is a compressive strain. We got the higher magnetizations, and this is when there is a tensile strain. We got lower magnetizations. So it clearly says there is a coupling of strain and magnetization in these films, and this has been done simultaneously at the polarized reflectometer instrument. And you know, at a fixed temperature, when there is a change, this magnetization and temperature for any ferromagnetic things, you get this kind of curve. So if you know at a particular temperature, if some magnetization is increasing, what does it say? It says there will be definitely change in the TC for that material. Okay, the same thing we are getting when we are applying a compressive strain, our magnetization has gone from here to here. So in fact, then later on we did this experiment, and we found that there is change in TC also, and we found a TC has increased by 6K when we applied a compressive strain of 0.011%. This is very small, but this is purely bending strain we have applied on this. So this clearly says that yes, there is a strain field which influence the magnetic and electronic property of these films, and this is only we have got from this PNR measurements. Okay. Okay, thank you. And tomorrow will be another class where I will show the another part of polarized neutron reflectivity, which is which I have explained in theory, which says that how to get the magnetic structure. Okay, so today we found magnetization depth profile, but no magnetic structure because we didn't do polarization analysis after reflected intensity from the sample. But tomorrow I will take the few examples where we have studied uh, 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 the samples where we really have seen how the magnetic structure is changing as a function of depth. Thank you. You want to say something? Anything? So tomorrow, same time, 3 o'clock, and we will see another set of examples which we can do by polarization. Yeah, and your assignment is already uploaded on Anuvidya. You please do those assignment and submit it as quickly as possible. Thank you.